Tonight, we drift toward Titan, Saturn's largest moon, a world so cold that oceans exist without water. Once imagined as a frozen, distant satellite, it reveals a reality far more unexpected. A moon where seas are carved from methane and familiar chemistry bends to unfamiliar rules. Welcome to Orbit for Sleep channel. Here, science moves slowly, quietly, and without urgency. Let us enter the orbit of science and drift gently towards sleep. You drift toward a distant moon orbiting Saturn, far from the warmth that keeps Earth's oceans alive. This is Titan. From a distance, it feels familiar in an unexpected way. A thick atmosphere wraps the surface, denser than Earth's, softening the sunlight into a permanent twilight. Clouds move slowly through the sky. A sharp horizon exists. It resembles a world that should hold water, a place where seas might quietly rest beneath an alien sky. For decades, scientists assumed that if any moon held an ocean, it would be water. On Earth, oceans feel inevitable. Children learn early that water gathers wherever gravity allows it. The idea feels intuitive, almost automatic. On Titan, that intuition quietly fails. When modern spacecraft finally peered through Titan's thick orange haze, radar images revealed something impossible. Smooth, dark regions near the poles. They flattened the landscape and traced shapes that looked unmistakably like coastlines. They behaved exactly like liquid. Yet, the environment told a conflicting story. The surface temperature is minus 180 degrees Celsius. At that extreme, water cannot flow. It freezes into ice as rigid as granite. So what is flowing? The liquids on Titan are methane and ethane. On Earth, methane is the invisible gas in our stoves. Ethane is a byproduct of fuel processing. To us, these are fuels, not landscapes. But on Titan, they change roles entirely. They become rivers, lakes, and seas. Rain falls there too. Not water, but liquid methane. It condenses in the cold sky, forms clouds, and washes over the surface. These alien rains carve channels through bedrock made of frozen water ice. Valleys form. Shorelines shift. The largest of these seas, Kraken Mare, stretches hundreds of kilometers. It holds more liquid hydrocarbons than all of Earth's oil and gas reserves combined. On a world where water is frozen stone, oil becomes the ocean. This discovery reshapes what the word ocean means. It is no longer defined by water alone. It is a stable body of liquid shaped by gravity, temperature, and chemistry. This realization carries a quiet weight. It proves that nature is not limited by Earth's example. The same physical laws create oceans in radically different forms. In the outer solar system, familiarity dissolves. What remains is a universe more flexible than we imagined, where temperature and chemistry quietly rewrite the rules of reality. You move closer to Titan's surface, where the idea of an ocean begins to lose its familiar meaning. The dark expanses near the poles look calm and heavy, spreading outward like seas on Earth. Their stillness suggests depth and weight, yet everything about the environment signals that these liquids cannot be water. On Titan, temperature governs all behavior. The surface remains near minus 180 degrees Celsius, a level of cold far beyond anything found naturally on Earth. At this temperature, water molecules are locked tightly together. Water becomes ice as hard as stone, forming Titan's bedrock, mountains, and plains. What flows instead must be made of something else. The oceans on Titan are composed primarily of methane and ethane. These are hydrocarbons, molecules built from carbon and hydrogen atoms bonded together in simple chains. Methane contains one carbon atom surrounded by hydrogen. Ethane contains two carbon atoms linked together, also surrounded by hydrogen. Their structures are basic, but under Titan's conditions, they behave in complex ways. On Earth, methane exists mostly as a gas. It escapes upward, rises into the atmosphere, and disperses quickly. Ethane is less common in daily life, usually encountered indirectly through industrial processes. Neither substance forms lakes or seas on Earth because temperatures are too high to keep them liquid. Titan reverses this relationship. Extreme cold slows molecular motion, allowing methane and ethane to condense, pool, and flow. This change is similar to how water behaves differently across Earth's climates. In polar regions, lakes freeze solid for much of the year. In warmer regions, the same water remains liquid and mobile. Titan represents the far end of this spectrum. The substances that are gases on Earth become liquids there, while water itself is permanently frozen. By analyzing how sunlight and radar signals reflected off the surface, scientists identified chemical signatures unique to methane and ethane. Spectroscopic measurements confirmed the composition of Titan seas. These measurements showed smooth liquid surfaces, gentle wave patterns, and evaporation consistent with hydrocarbons rather than water. Ethane plays a particularly important role. Over long periods, sunlight breaks apart methane in Titan's upper atmosphere. Some of that methane reforms, while some combines into heavier hydrocarbons, including ethane. Gravity pulls these molecules downward, where they accumulate in lakes and seas. Titan's oceans are therefore not static reservoirs. They are part of a slow chemical circulation connecting sky and surface. In everyday terms, Titan seas resemble a world-sized version of Earth's fuel storage, except exposed openly to the environment. A substance that powers engines and heats homes on Earth quietly shapes coastlines and shorelines on Titan. The same chemistry supports industry in one world and geography in another. Understanding what Titan's oceans are made of expands the concept of planetary liquids. It shows that oceans are not defined by a single substance, but by conditions. Wherever temperature, pressure, and chemistry align, a planet or moon can sustain seas made from materials that feel ordinary in one context and extraordinary in another. You follow Titan's curved surface as it slowly rotates beneath its thick atmosphere. From above, the moon appears calm and uniform, wrapped in layers of haze that blur fine details. But as observation techniques improved, patterns began to emerge. The oceans on Titan are not spread evenly across the globe. They gather in specific regions, shaped by climate, seasons, and long-term circulation. Most of Titan's large seas are concentrated near the North Pole. This region holds the majority of known liquid bodies, including Kraken Mare, Ligeia Mare, and Punga Mare. Together, they form a network of interconnected lakes and seas that resemble an Arctic archipelago. Shorelines curve gently, narrow channels connect larger basins. The geography suggests stability rather than temporary flooding. The South Pole tells a different story. There, only a few small lakes appear, scattered and shallow. Some seem to dry up over time, leaving behind empty depressions. This imbalance puzzled scientists at first. If methane rain falls across Titan, liquids might be expected to collect equally at both poles. The explanation lies in Titan's seasons and atmosphere. Titan orbits the Sun once every 29 Earth years, sharing Saturn's long seasonal cycle. Each pole experiences extended periods of sunlight, followed by long darkness. Over time, methane evaporates more efficiently in the summer hemisphere and migrates through the atmosphere toward the winter pole, where it condenses and falls as rain. At present, Titan's northern hemisphere serves as the long-term reservoir for liquid hydrocarbons. Methane clouds drift northward, releasing rain that replenishes lakes and seas. In the south, evaporation gradually outpaces rainfall, shrinking surface liquids. This process unfolds slowly, over decades, creating an uneven but predictable distribution. Topography also plays a role. Radar mapping reveals that the northern polar region contains broad, low-lying basins well-suited for liquid accumulation. These basins act like natural bowls, collecting hydrocarbons the way Earth's oceans fill tectonic depressions. In contrast, Titan's equatorial regions are higher and drier, marked by vast fields of hydrocarbon dunes rather than lakes. Those equatorial dunes are made of solid organic particles, similar in size to sand grains. Winds push them into long, parallel ridges that stretch for hundreds of kilometers. The presence of dunes instead of seas reinforces the idea that Titan's surface liquids are climate-controlled rather than globally distributed. Seen as a whole, Titan's seas behave less like random spills and more like a planetary system. Liquids move from sky to ground, from equator to pole, and from one hemisphere to the other across long stretches of time. The oceans exist not everywhere, but where Titan's slow rhythms allow them to persist. You remain above Titan's surface, but direct sight is impossible. A thick atmosphere blocks visible light, scattering it into a permanent orange haze. Ordinary cameras cannot see through it. For a long time, Titan concealed its surface completely, leaving only guesses about what lay below. The breakthrough came when scientists began to rely on instruments that do not depend on sight alone. Radar became the key. Radar sends radio waves toward the surface and measures how they return. Smooth surfaces reflect radar strongly and evenly. Rough or solid terrain scatters the signal. When radar maps of Titan were first assembled in the late 20th century and early 21st century, certain regions behaved differently from the rest of the Moon. Near the poles, radar reflections appeared unusually dark and uniform. These regions absorbed signals rather than scattering them, a signature consistent with liquid surfaces. As mapping continued, the shapes of these dark areas grew more precise. They formed enclosed basins, branching channels, and curved shorelines. The geometry matched how liquids settle under gravity. Solid ice or rock does not naturally create such smooth, level boundaries across large distances. Additional confirmation came from specular reflection, a mirror-like radar return. In certain observations, radar signals bounce directly back from Titan's surface at specific angles. This effect occurs when a surface is flat and liquid, similar to sunlight reflecting off a calm lake on Earth. These reflections provided some of the strongest evidence that Titan's seas were not frozen solids, but active liquids. Infrared spectroscopy added another layer of certainty. By analyzing how different wavelengths of light were absorbed and emitted, scientists identified chemical fingerprints on the surface. These fingerprints matched methane and ethane rather than water. The data showed evaporation patterns consistent with hydrocarbon cycling between surface and atmosphere. Altimetry measurements further strengthened the case. By timing how long radar pulses took to return, scientists measured surface elevations. The liquid bodies sat at consistent gravitational levels, just as oceans and seas do on Earth. Separate lakes share the same reference height, indicating connected fluid systems rather than isolated patches. Together, these methods formed a coherent picture. Radar shape, reflection strength, chemical signatures, and elevation all pointed toward the same conclusion. Titan's dark polar regions were not shadows, not ice fields, and not solid plains. They were seas. The confirmation did not come from a single image or moment. It emerged slowly, through repeated passes and overlapping measurements. PAGA revealed its oceans not by becoming clearer, but by responding predictably to the tools designed to listen rather than look. Titan's seas exist in their unusual form because temperature controls which substances can remain liquid. At Titan's distance from the Sun, solar energy is weak. The surface receives only a small fraction of the heat that reaches Earth. As a result, average temperatures remain near -180 degrees Celsius, shaping every physical and chemical process on the Moon. Water molecules require relatively high temperatures to move freely. On Earth, water freezes at 0 degrees Celsius, a point familiar from daily life. Below that threshold, molecular motion slows and liquid water becomes solid ice. On Titan, temperatures are so low that water behaves not as a fluid, but as a structural material. It forms the crust, mountains, and bedrock of the Moon, functioning more like stone than ice. Methane and ethane respond differently to extreme cold. These hydrocarbons have much lower freezing points than water. Methane freezes near -182 degrees Celsius, and ethane freezes even lower. Titan's surface temperature lies just above these limits, allowing both substances to remain liquid for long periods. In this narrow thermal window, hydrocarbons become the most stable surface liquids available. Pressure also plays a role. Titan's atmosphere is denser than Earth's, exerting greater surface pressure despite the Moon's smaller size. This added pressure helps stabilize liquid methane and ethane, reducing evaporation and allowing lakes and seas to persist. The combination of low temperature and sufficient pressure creates conditions where hydrocarbons can collect rather than disperse. This situation mirrors familiar processes on Earth, but with different materials. On Earth, water circulates between solid, liquid, and gas depending on climate. In colder regions, water freezes into ice caps. In warmer regions, it flows freely as rivers and oceans. Titan follows the same physical rules. The substances that change phase are simply not the ones humans expect. Chemical abundance reinforces this outcome. Titan's atmosphere contains large amounts of methane, continually replenished through internal and atmospheric processes. Sunlight breaks methane apart in the upper atmosphere, but some of it reforms, while heavier hydrocarbons like ethane accumulate and fall to the surface. Over long timescales, this steady supply ensures that hydrocarbons remain available to fill basins and lowlands. The absence of liquid water on Titan's surface is therefore not a mystery or anomaly. It is the natural result of environmental conditions. Where Earth's climate allows water to dominate, Titan's climate selects hydrocarbons instead. The same laws of physics apply, but they operate in a colder regime. Titan's oil seeps demonstrate that planetary environments do not choose substances based on familiarity. They select materials based on stability. Wherever temperature and pressure align, liquids will form, whether they are made of water, methane, or substances rarely encountered in everyday human experience. Titan's surface liquids cannot be understood without considering its atmosphere. Titan possesses one of the thickest atmospheres among moons in the solar system, composed primarily of nitrogen, with methane as the most important secondary component. This dense atmospheric blanket regulates temperature, pressure, and the movement of chemicals between sky and ground. Methane on Titan plays a role similar to water vapor on Earth. It evaporates from lakes and seas, rises into the atmosphere, condenses into clouds, and eventually falls back to the surface as rain. This process is known as the methane cycle. While the materials differ, the underlying physics mirrors Earth's water cycle. Solar energy drives this circulation. Even though sunlight at Saturn's distance is weak, it provides enough energy to evaporate methane from Titan's seas. Methane molecules escape the surface, drift upward, and cool as they rise. In colder regions of the atmosphere, they condense into clouds composed of tiny liquid droplets. These clouds are not evenly distributed. Observations show that methane clouds form preferentially near the poles and during certain seasonal periods. When conditions align, methane rain falls, sometimes gently, sometimes in intense storms capable of reshaping the surface. Channels carved into the icy crust indicate repeated rainfall events over long spans of time. Unlike Earth's water cycle, Titan's methane cycle is chemically unstable. Sunlight in the upper atmosphere breaks methane molecules apart through a process called photolysis. Over time, this destruction should deplete methane entirely. The fact that methane remains abundant indicates continuous replenishment. Several mechanisms are thought to supply new methane. One possibility involves subsurface reservoirs where methane is trapped within icy layers. Cryovolcanic activity may release methane from the interior, allowing it to escape into the atmosphere. Another possibility is slow chemical release from deep underground structures formed early in Titan's history. As methane circulates, some of it transforms into heavier hydrocarbons. These molecules fall as organic haze or liquid ethane, accumulating on the surface and contributing to Titan's seas. The methane cycle therefore connects atmospheric chemistry directly to surface geology. In everyday terms, Titan operates like a planet-sized distillation system. Gases rise, cool, condense, and return, while chemical byproducts gradually collect below. This slow, persistent circulation maintains Titan's lakes, seas, and dunes. The methane cycle gives Titan long-term stability. Without it, surface liquids would vanish and the moon would become dry and static. Instead, Titan remains active, shaped continuously by interactions between atmosphere, surface, and interior, following the same physical rules that govern climates across the solar system. Titan's surface shows clear evidence of erosion and transport, indicating that liquid flow has shaped the landscape over long periods of time. Channels, valleys, and branching networks appear across wide regions, especially near the poles. These features follow patterns familiar from Earth, even though the materials involved are entirely different. The rivers on Titan are carved not by water, but by liquid methane and ethane. Radar imagery reveals sinuous channels that cut through the icy crust, sometimes extending hundreds of kilometers. Their shapes indicate sustained flow rather than brief flooding. Over time, repeated liquid movement sculpts the surface, deepening channels and smoothing surrounding terrain. Methane rain is the primary source of this erosion. As methane evaporates from lakes and seas, it condenses into clouds and eventually falls back to the surface. Rainfall does not occur constantly, but in episodic events linked to Titan's seasonal cycles. When rain does fall, It can be intense, delivering enough liquid to rapidly alter the landscape. Because water ice on Titan behaves like solid rock, hydrocarbon rivers eroded in ways similar to how water erodes stone on Earth. Channels widen, bends form, and sediment is transported downstream. Over time, these processes create recognizable drainage basins and floodplains, despite the extreme cold. At lower elevations, rivers terminate in lakes and seas, forming shorelines that shift gradually as liquid levels change. Radar measurements show smooth, gently sloping boundaries consistent with stable liquid surfaces. Some shorelines appear terraced, suggesting long-term fluctuations in sea level driven by climate changes. In certain regions, dry channels can be seen extending towards empty basins. These features indicate that Titan's climate has not always remained constant. Periods of increased rainfall likely filled lakes that later partially evaporated, leaving behind exposed shorelines and abandoned river paths. The interaction between rainfall, rivers, and seas forms a complete surface system. Liquids fall from the sky, move across the land, and collect in low-lying areas. This cycle mirrors Earth's hydrological processes, even though the substances involved differ. From a geological perspective, Titan's hydrocarbon rivers demonstrate that familiar landforms do not require familiar materials. Given enough time and repeated flow, liquids of many kinds can shape worlds in predictable ways. Titan's surface records these processes quietly, preserving the history of its climate in channels and shores made of hydrocarbons rather than water. Beneath Titan's frozen surface, evidence suggests the presence of another ocean, one that contrasts sharply with the hydrocarbon seas above. This hidden ocean is not made of methane or ethane, but of water. Unlike Titan's surface liquids, this water remains locked away, buried deep beneath layers of ice. Hades' crust is composed primarily of water ice, but under the extreme pressures found below the surface, ice behaves differently than it does on Earth. As depth increases, pressure rises, allowing water to remain liquid even at very low temperatures. In this environment, a subsurface ocean can persist without freezing solid. Multiple lines of evidence support the existence of this internal ocean. Measurements of Titan's gravity fields show subtle variations that indicate a layered interior rather than a fully solid body. These variations suggest that Titan's outer shell floats above a denser, deformable layer, consistent with the global ocean beneath the ice. Observations of Titan's rotation provide further clues. Titan does not rotate as a perfectly rigid object. Slight shifts in its rotational behavior imply that the outer ice shell is mechanically decoupled from the interior. This decoupling is most easily explained by a liquid layer separating the two. The composition of this subsurface ocean is likely water mixed with ammonia and salts. Ammonia lowers the freezing point of water, allowing the ocean to remain liquid at temperatures that would otherwise cause complete freezing. This chemical mixture increases the stability of the hidden ocean over geological timescales. The existence of a water ocean beneath the ice introduces a striking contrast within Titan. On the surface, hydrocarbons circulate through atmosphere and land. Below, water dominates in silence, isolated from direct contact with the environment above. The two systems remain largely separate, connected only through slow internal processes. This buried ocean also raises questions about long-term chemical exchange. Cryovolcanic activity may occasionally transport material from the interior upward, releasing water or ammonia onto the surface. Such events would be rare, but over millions of years they could influence Titan's atmospheric composition. From a broader perspective, Titan joins a growing group of icy worlds believed to harbor subsurface oceans. These hidden reservoirs expand the number of places in the solar system where liquid water can exist, even far from the sun. Titan demonstrates that oceans do not always announce themselves on the surface. Some remain concealed, shaped by pressure, chemistry, and time beneath a frozen shell. Titan's atmosphere is permanently wrapped in a thick orange haze, obscuring the surface and filtering sunlight before it reaches the ground. This haze is not a cloud layer in the traditional sense, but a complex chemical product created high in the atmosphere. It plays a central role in Titan's climate, chemistry, and long-term evolution. The process begins when sunlight and energetic particles from Saturn interact with methane and nitrogen in Titan's upper atmosphere. These energy sources break molecular bonds through chemical reactions known as photochemistry. Methane molecules split apart, nitrogen becomes reactive, and new compounds begin to form. As these fragments recombine, they create increasingly complex organic molecules. Simple hydrocarbons link into longer chains. Nitrogen atoms insert themselves into these structures, producing nitriles and other nitrogen-bearing compounds. Over time, this chemistry generates large, carbon-rich molecules collectively known as tholins. Tholins are not a single substance, but a mixture of complex organic materials. They absorb visible light efficiently, giving Titan its characteristic orange-brown appearance. Suspended in the atmosphere as fine particles, they scatter and dim sunlight, reducing the amount of energy that reaches the surface. This contributes to Titan's cold climate and stabilizes its surface liquids. As haze particles grow heavier, they slowly drift downward. Eventually, they settle onto the surface, coating ice, dunes, and shorelines with a thin layer of organic material. This steady fallout connects atmospheric chemistry directly to surface composition. In everyday terms, Titan's haze functions like a planet-wide chemical factory. Energy enters at the top, raw materials are transformed in stages, and products accumulate below. On Earth, similar processes occur in polluted urban air or inside industrial reactors, but on Titan, the scale is global and uninterrupted. The haze also preserves chemical history. Each particle carries information about the reactions that formed it and the conditions under which it evolved. By studying the composition of these particles, scientists gain insight into Titan's atmospheric balance and long-term stability. Titan's orange haze demonstrates that atmospheres are not passive blankets of gas. They are active chemical systems capable of generating complex organic matter. In Titan's case, this chemistry operates continuously, shaping the moon's appearance, regulating its climate, and supplying the surface with materials formed high above, far from direct contact with land or sea. Titan is often described as a chemical echo of early Earth. This comparison does not rely on appearance or temperature, but on atmosphere composition and surface chemistry. Long before oxygen reshaped Earth's environment, the planet's atmosphere was dominated by nitrogen and simple carbon-based molecules. Titan preserves a similar state, frozen in a colder setting. In Earth's distant past, during the 20th century's early models of planetary evolution and later refined studies, scientists reconstructed an atmosphere rich in nitrogen, methane, and other reduced gases. Oxygen was scarce, and complex life had not yet emerged. Under those conditions, sunlight drove chemical reactions that produced increasingly complex organic molecules. Titan operates under comparable chemical rules. Its atmosphere is primarily nitrogen, with methane acting as the key reactive ingredient. Sunlight initiates reactions that break methane apart and allow carbon to recombine into more complex structures. The resulting organic compounds resemble those thought to have existed on early Earth before biological processes took over. The surface environments also show parallels. On early Earth, liquid water collected organic molecules delivered by atmospheric reactions and geological activity. These molecules interacted in lakes, shorelines, and shallow seas. On Titan, liquid methane and ethane play a similar collecting role, gathering organic material produced in the atmosphere and concentrating it on the surface. Despite these similarities, the differences are critical. Early Earth was warm enough for water to remain liquid, enabling rapid chemical interactions. Titan's extreme cold slows chemical reactions dramatically. Processes that might occur in days or years on Earth unfold over thousands or millions of years on Titan. This slowdown, however, offers a scientific advantage. Titan acts as a natural archive. Chemical pathways that may have been erased or overwritten on Earth by biological activity remain preserved on Titan's surface and in its atmosphere. The absence of life allows prebiotic chemistry to persist without disruption. In practical terms, Titan provides scientists with a controlled comparison. It shows how far chemistry can progress toward complexity without biology. By studying Titan, researchers refine models of Earth's earliest stages and identify which chemical steps require liquid water and which can occur in alternative solvents. Titan does not replicate early Earth, it reframes it. By presenting similar chemistry under different physical conditions, Titan helps isolate the factors that transformed a lifeless planet into one capable of supporting biology. In doing so, it offers a rare window into a chapter of Earth's history that no longer exists on our own world. The presence of liquid methane and ethane on Titan forces a careful reconsideration of what life requires. On Earth, Every known form of life depends on liquid water. Water dissolves chemicals, transports nutrients, and allows complex reactions to occur efficiently. This dependence has shaped biology so completely that water is often treated as a universal requirement rather than a local condition. From a chemical perspective, water is an effective solvent because of its polarity. It separates charged molecules, stabilizes complex structures, and supports rapid reaction cycles. These properties make water ideal for life on Earth. Titan, however, operates under a different chemical regime. At extremely low temperatures, water loses its usefulness as a solvent, while hydrocarbons remain liquid and mobile. Liquid methane and ethane are nonpolar solvents. They do not dissolve substances in the same way water does. Reactions proceed more slowly, and many familiar biological processes cannot function. Yet slow chemistry is not the same as impossible chemistry. Under Titan's conditions, molecular interactions still occur, governed by the same physical laws but operating on different timescales. Laboratory studies have explored how simple organic molecules behave in liquid methane. These experiments show that membranes, compartments, and repeating chemical patterns can theoretically form even without water. While these structures differ fundamentally from Earth-based cells, they demonstrate that organization does not require a single solvent. Everyday experience provides a useful analogy. On Earth, life thrives in environments once considered uninhabitable, including deep-sea hydrothermal vents and acidic lakes. These discoveries did not change the laws of biology, but they expanded the range of conditions under which life can persist. Titan extends that expansion further, beyond water itself. The question is not whether Titan hosts life similar to Earth's. Its temperature and chemistry make that unlikely. The more relevant consideration is whether alternative biochemical systems could exist, operating slowly, quietly, and invisibly by human standards. Titan offers a natural test case for this idea. It combines stable liquid environments, abundant organic chemistry, and long timescales. Even if life never arises there, Titan demonstrates that habitability cannot be defined by a single example. By studying Titan, scientists refine the boundary between chemistry and biology. The Moon shows that water-based life is one solution, not a universal rule. In doing so, Titan reshapes how life is sat for beyond Earth, encouraging definitions based on physical possibility rather than familiarity. Titan provides a setting where complex organic chemistry unfolds without interference from biological life. This makes the Moon a natural laboratory for studying prebiotic chemistry, the stage of chemical evolution that precedes living systems. Conditions that no longer exist on Earth remain accessible on Titan, preserved by cold and time. In Titan's upper atmosphere, sunlight and energetic particles continuously drive chemical reactions. Methane and nitrogen break apart and recombine into increasingly complex organic molecules. These reactions occur without enzymes, cells, or genetic material guiding them. The process reveals what chemistry can achieve on its own, governed only by physical laws. As newly formed organic compounds descend through the atmosphere, they accumulate on the surface. Liquid methane and ethane act as collection media, concentrating molecules that would otherwise remain dispersed. Shorelines, lake beds, and sediment layers become sites where chemistry can persist and interact over long periods. On early Earth, similar chemistry likely occurred, but it was later obscured by biological activity. Life consumes, modifies, and recycles organic material, erasing evidence of earlier chemical stages. Titan lacks this complication. Its chemistry proceeds without competition, allowing intermediate products to remain intact. Laboratory simulations on Earth attempt to replicate these conditions. Scientists recreate Titan-like atmospheres and expose them to ultraviolet light, producing organic solids similar to those observed on the Moon. These experiments confirm that Titan's environment naturally generates molecules relevant to prebiotic processes. The slow pace of Titan's chemistry is a defining feature. Low temperatures reduce reaction rates, stretching chemical evolution across immense timescales. While this limits biological potential, it enhances scientific clarity. Processes unfold gradually, making cause and effect relationships easier to isolate. Titan's value as a laboratory lies in its completeness. Atmosphere, surface liquids, solid materials, and internal processes all contribute to a closed chemical system. Studying one component helps explain the others, forming a coherent picture of chemical evolution without life. By observing Titan, scientists refine models of how complex chemistry emerges from simple beginnings. The moon demonstrates that many steps toward biological complexity occur naturally, long before life appears. Titan does not explain how life begins, but it reveals how far chemistry can progress on its own, given stability, energy, and time. For much of modern astronomy, the concept of habitability has been tightly linked to Earth-like conditions. A habitable world was defined by the presence of liquid water on the surface, moderate temperatures, and a stable atmosphere. These criteria emerged from a single data point: Earth itself. Titan challenges this framework by meeting some expectations while violating others. It possesses a thick, stable atmosphere, long-term surface liquids, and active chemical cycles. At the same time, its surface temperature is far below the range traditionally associated with life, and its liquids are hydrocarbons rather than water. This contrast forces a separation between two ideas often treated as identical: Earth-like and habitable. Earth-like conditions describe familiarity. Habitability describes the potential for sustained chemical complexity. Titan demonstrates that these concepts do not always overlap. From a physical standpoint, habitability depends on stability and energy flow. A world must maintain liquid environments over long periods, allow chemical interactions to recur, and avoid rapid loss of key materials. Titan satisfies these requirements in an unconventional way. Its methane cycle, dense atmosphere, and slow climate evolution provide continuity, even in extreme cold. In everyday terms, this is similar to recognizing that life-supporting systems can operate under different settings. A refrigerator preserves food through cold rather than heat. The function remains, even though the conditions differ. Titan applies this principle on a planetary scale. This broader definition alters how distant worlds are evaluated. Planets and moons once dismissed as too cold or too alien gain renewed interest when examined through the lens of chemical stability rather than surface comfort. Titan becomes a reference point for identifying alternative pathways to complexity. The shift does not imply that Titan is likely inhabited. Instead, it refines the criteria used to assess other worlds. By expanding the definition of habitability beyond water and warmth, Titan increases the number of environments considered scientifically meaningful. In this way, Titan changes not only how habitability is defined, but how exploration priorities are set. It encourages a move away from searching only for Earth's reflection and toward understanding the full range of conditions under which organized, persistent systems can exist in the universe. Titan reframes the idea of energy and resources by separating usefulness from habitability. On Earth, energy resources such as oil, coal, and natural gas are products of biological history. They originate from ancient life, compressed and transformed over geological time. On Titan, similar materials exist without biology. Titan's lakes and seas contain vast quantities of methane and ethane, distributed naturally across the surface. These hydrocarbons are not stored underground or trapped in rock. They are openly exposed, cycling between atmosphere and surface. From a purely chemical perspective, Titan holds an amount of accessible hydrocarbon energy that exceeds Earth's known reserves. This abundance highlights a fundamental distinction. On Earth, hydrocarbons are scarce because they depend on life. On Titan, they are common because they arise from atmospheric chemistry driven by sunlight. Energy-rich molecules do not require biology to exist. They require the right chemical pathways and sufficient time. In everyday terms, this difference is similar to comparing handcrafted fuel to naturally accumulating rainwater. On Earth, hydrocarbons must be extracted carefully from specific locations. On Titan, they pool naturally wherever conditions allow. The process is slow but continuous. Titan also demonstrates that energy availability does not imply usability. While methane is an efficient fuel on Earth, Titan's extreme cold limits how energy could be accessed or converted. Combustion requires oxygen, which Titan lacks. Any theoretical use of hydrocarbons there would rely on unfamiliar technologies and external energy sources. From a scientific perspective, this contrast is instructive. It separates the concept of energy storage from energy exploitation. A world can be rich in chemical energy while remaining hostile to technological activity. Resource abundance alone does not lead to development or civilization. Titan therefore offers a cautionary comparison. It shows that energy resources are contextual. Their value depends on environment, chemistry, and available mechanisms for release. What powers modern civilization on Earth becomes a passive geological feature on another world. By studying Titan, scientists gain perspective on how energy systems emerge, persist, and remain unused. The Moon illustrates that the universe produces energy-rich environments freely, but whether those environments become active depends on conditions far beyond the presence of fuel alone. Future exploration of Titan focuses on direct interaction with its surface and atmosphere, moving beyond remote observation. The goal is not only to confirm what Titan seas are made of, but to measure how they behave over time and how they interact with the environment around them. One major shift in mission design involves mobility. Earlier spacecraft observed Titan from orbit or during brief flybys. Upcoming concepts emphasize long-duration presence, allowing instruments to remain active through seasonal changes. This approach enables the study of evaporation, rainfall, shoreline movement, and chemical exchange across extended periods. Atmospheric entry is a central challenge. Titan's dense atmosphere, composed largely of nitrogen, provides both obstacles and advantages. It slows incoming spacecraft effectively, reducing heat loads during descent. At the same time, thick haze limits visibility, requiring navigation systems that rely on radar and inertial guidance rather than optical cameras. Several mission concepts target Titan's polar seas directly. Floating probes and autonomous surface vehicles are designed to land gently on methane, ethane liquids, remaining buoyant while collecting samples. These platforms would analyze liquid composition, temperature gradients, wave activity, and dissolved organic material. Aerial exploration also plays a key role. Rotorcraft-style vehicles take advantage of Titan's low gravity and dense air, which make powered flight more efficient than on Earth. These vehicles can travel between dunes, shorelines, and liquid bodies, linking atmospheric chemistry to surface features in a single mission. Energy supply is another critical consideration. Solar power is weak at Saturn's distance, making nuclear-based systems the most reliable option. These power sources allow continuous operation independent of sunlight, enabling instruments to function during Titan's long nights and seasonal darkness. Data from future missions would transform Titan from a theoretical case study into a measured system. Direct sampling would test models of hydrocarbon chemistry, confirm rates of methane loss and replenishment, and clarify the relationship between surface liquids and the subsurface ocean. Titan seas represent more than a destination. They are a proving ground for exploration strategies suited to extreme environments. Techniques developed there will inform missions to other cold, distant worlds, expanding how and where robotic exploration can operate across the solar system. Comparing Titan's oceans to Earth's seas reveals how the same physical principles produce very different outcomes under different conditions. Both worlds host stable bodies of liquid shaped by gravity, topography, and climate. The similarities end there, while the contrasts clarify what an ocean fundamentally is. On Earth, oceans are composed of liquid water, a polar solvent that dissolves salts, gases, and organic molecules efficiently. This chemical flexibility allows rapid reactions and supports complex ecosystems. Temperature ranges keep water cycling easily between solid, liquid, and gas, driving weather and climate. Titan's oceans are composed primarily of methane and ethane. These hydrocarbons are non-polar liquids with limited dissolving power compared to water. Chemical reactions proceed more slowly, and many Earth-like processes do not occur. Yet these liquids still flow, pool, evaporate, and condense, following the same thermodynamic rules. Density and buoyancy differ as well. Ice on Earth floats in water, creating polar ice caps and seasonal melt. On Titan, water ice is denser than liquid hydrocarbons and sinks rather than floats. This inversion alters shoreline behavior, sediment transport, and the structure of coastlines. Energy exchange also contrasts sharply. Earth's oceans absorb sunlight efficiently, storing heat and redistributing it through currents. Titan's seas receive far less solar energy and remain close to ambient temperature. Wave activity exists, but it is subdued, shaped by low winds and low gravity. Salinity provides another point of comparison. Earth's oceans are saline due to dissolved minerals from continental erosion. Titan's seas contain dissolved organic compounds produced in the atmosphere. Instead of salt cycles, Titan exhibits organic accumulation, slowly enriching its liquids over time. In everyday terms, Earth's oceans function like an active engine, constantly moving heat and material. Titan's seas resemble a slow reservoir, stable and persistent, changing gradually rather than dynamically. This comparison demonstrates that oceans are not defined by composition alone. They are defined by persistence, scale, and interaction with the planet's environment. Earth and Titan represent two valid expressions of the same concept, shaped by temperature, chemistry, and distance from the Sun rather than by a single preferred substance. Within the solar system, Titan's oil oceans occupy a unique position. Many worlds contain liquids, but the substances, locations, and roles of those liquids vary widely. By placing Titan alongside other planets and moons, its distinctiveness becomes clearer. Earth hosts surface oceans of water maintained by moderate temperatures and strong solar input. Mars once held liquid water on its surface, but declining atmospheric pressure and cooling led to widespread loss. Venus may have had early oceans, but intense greenhouse heating removed surface liquids entirely. In each case, water dominates the story, even when it disappears. Beyond the inner planets, liquid environments take different forms. Jupiter and Saturn possess deep layers of liquid hydrogen and helium, but these exist under extreme pressures and temperatures far removed from surface conditions. Uranus and Neptune contain internal oceans of water, ammonia, and methane mixtures, buried beneath thick atmospheres and ice layers. Several icy moons are believed to host subsurface water oceans. Europa, Enceladus, and Ganymede likely maintain liquid water beneath their icy shells, warmed by tidal heating. These oceans are hidden, sealed off from direct contact with space, and detectable only through indirect measurements. Titan stands apart because its liquids exist openly on the surface and are not made of water. No other known body in the solar system combines a dense atmosphere, stable surface liquids, and complex organic chemistry in this way. Titan's seas interact directly with weather, erosion, and atmospheric processes, forming a complete surface system. This combination places Titan between categories. It is neither a typical icy moon nor a terrestrial planet. Its oil oceans operate at the interface between atmosphere and ground, a role usually reserved for water on Earth. From a comparative perspective, Titan expands the inventory of planetary liquids. It shows that oceans can exist wherever temperature and pressure allow a substance to remain liquid for long periods. The specific substance depends on local conditions rather than universal preference. In the broader context of the solar system, Titan demonstrates that familiar planetary features can arise through unfamiliar materials. Oil oceans are not anomalies, but logical outcomes of chemistry and climate operating far from the Sun. Titan's position reveals how diverse the expressions of planetary environments can be within a single star system. Titan consistently challenges human intuition because it inverts assumptions built from life on Earth. Many expectations about planets and moons arise from everyday experience with warmth, liquid water, and familiar materials. Titan operates under the same physical laws, yet produces outcomes that feel counterintuitive. On Earth, cold is associated with inactivity. Frozen landscapes suggest stillness and permanence. On Titan, extreme cold does not halt motion. It selects different materials to move. Methane flows where water cannot. Ice behaves like rock. Landscapes evolve not despite the cold, but because of it. Another intuitive assumption links atmosphere to warmth. Thick atmospheres on Earth trap heat, raising temperatures. Titan's dense atmosphere does provide insulation, yet the weak sunlight at Saturn's distance dominates the energy balance. The result is a world with active weather but persistent cold. Clouds form, rain falls, and winds shape dunes, all without warming the surface. Human intuition also ties oceans to life. On Earth, seas teem with biological activity and support complex ecosystems. Titan's oceans are quiet by comparison. They contain energy-rich molecules but lack the chemical conditions required for familiar biology. The presence of oceans does not imply abundance of life. It implies only the presence of stability. Scale further complicates perception. Geological change on Earth often appears rapid because human lifespans are short. On Titan, processes unfold over much longer timescales. Shorelines shift slowly. chemical cycles progress gradually. Change exists, but patience is required to recognize it. Everyday analogies help clarify this mismatch. A refrigerator preserves food by slowing chemical reactions rather than stopping them. Titan functions similarly at a planetary scale. Activity continues, but at a pace that defies human expectations of motion and productivity. Titan's greatest challenge is not technological, but conceptual. It reveals that intuition shaped by one environment cannot reliably predict behavior in another. When temperature, pressure, and chemistry change together, familiar categories lose meaning. By confronting these limits of intuition, Titan becomes more than an object of study. It serves as a corrective lens, reminding observers that understanding the universe requires abandoning assumptions formed in comfort and replacing them with principles that hold across vastly different conditions. Titan offers a perspective on life that extends beyond specific organisms or environments. Rather than answering whether life exists there, Titan reshapes how life is considered across the universe. It shifts attention from familiar outcomes to underlying conditions. For much of scientific history, the search for life has focused on Earth-like signals. Liquid water, moderate temperatures, and atmospheric oxygen became primary indicators. These markers remain valuable, but they reflect a narrow sample. Titan demonstrates that complex chemistry can persist far outside this comfort zone. Life, at its core, depends on organized chemical processes sustained over time. These processes require energy gradients, stable environments, and materials capable of forming complex structures. Titan satisfies some of these requirements while lacking others, highlighting that life-related conditions exist along a spectrum rather than at a single threshold. In practical terms, this is similar to recognizing that different machines require different operating ranges. An engine designed for heat fails in cold, while another built for low temperatures functions efficiently. The presence of activity depends on compatibility, not universality. Titan suggests that life elsewhere may operate under conditions incompatible with Earth-based biology. This realization influences how distant worlds are interpreted. A planet or moon that lacks water or warmth is no longer automatically excluded. Instead, scientists evaluate whether alternative solvents, slow chemistry, or unfamiliar energy pathways could support organized systems. Titan also emphasizes the role of time. In cold environments, chemical evolution proceeds slowly. While this limits rapid development, it allows stability across immense durations. Life, if it emerges under such conditions, may evolve at a pace difficult to detect or recognize. The broader implication is restraint. Titan cautions against assuming that life must announce itself clearly or resemble known examples. It encourages definitions grounded in physics and chemistry rather than expectation. By expanding the range of plausible environments, Titan changes the search for life from a hunt for mirrors into an exploration of diversity. It suggests that the universe may host forms of organization shaped by conditions unlike any found on Earth, quietly operating according to the same fundamental laws.